Hello everyone, welcome back to the series of tutorials on geostatistics. Today we'll play a game to build intuition on the concept of spatial correlation. The game goes as follows. Suppose that we're given a real-world satellite image and are asked to describe its spatial correlation. Although this task seems simple, many people get confused by the concept. So our goal here is to address two questions. What do we mean by spatial correlation? And second, is there any way that we can describe this spatial correlation properly without actually crunching numbers and by just looking at the image? Here, what you see is an image from Peru that was taken from the Google Earth Engine view website. And you can slide this slider here to get different images from Google Earth. In particular, I suggested these three images here, 68, 487, and 214. Because they provide good insights on what we're going to show next. So let me go back to image 68. And as you can see, it seems like a mine looked from the top. In order to define spatial correlation of this image, we need to go back into basic statistics and recall the concept of Pearson correlation. So given two variables, x and y, which are jointly sampled into a dataset, x1, y1, x2, y2, until xn, yn. We can compute an estimate of this Pearson correlation by using this formula, where the index I here loops over the pixels of the image. So for example, if I take my variable x to be the red channel of the image, and my variable y to be the blue channel of the image, I can produce the scatter plot between these two variables here at the bottom. And I can compute this regression line in red, which has an inclination which is equal to this correlation coefficient, in this case 0.88. You see that the calculation of the correlation coefficient uses one pixel at a time. So effectively what we do is we need to get this matrix of x values and vectorize it to make it a flat vector before we call the correlation function. Now, in order to define spatial correlation, we'll need to build a different concept first. But before we do that, there's another comment that I would like to make here, because strictly speaking, using the red and blue channels of an RGB space is not allowed, let's say, if you want to take into account the fact that these channels are coupled. So for illustration purpose, I'm using the red and blue channels, or any other channel for that matter here, to produce these scatter plots. But the correlations we're getting are not necessarily reflecting valid correlations. They can be spurious because this RGB space has some complications to it. So we can just ignore it for the purpose of the tutorial, but think about these variables as actual geophysical variables, like the vegetation index or anything that you can actually compute using remote sensing. In order to generalize this to spatial correlation, let's go now to the concept of the age scatter plot. The age scatter plot is a generalization in the sense that you produce a new data set of x and y's, but now you're allowed to have different pixels for the primary variable x and for the secondary variable y. So now you're looping the index I for variable x and the index j for variable y. In particular, we are interested in producing data sets such that the pairs of pixels I and j are located age units apart. So this arrow notation here is what I'm illustrating with this picture here. I get a crop from my Peru image, and I introduce this concept of the arrow, where at the head of the arrow I have my pixel I, and at the tail of the arrow I have my pixel j. We can produce a data set by sliding this arrow over the image, and every time we move to a separate pixel, we get a different value for xy, xi, and a different value for yj. We can denote this head variable by age, which can be either x or y. And similarly, denote the tail variable by t, which can again be either x or y. We can look at the samples by creating this spatial data set with the georef function from GeoStats, where I'm georeferencing these two images, these channels, into a coordinate system. And then I'm sampling 5,000 samples from this image to produce a smaller sample for quick interactions. So the concept of the age scatter plot, which is this function that you see here at the bottom, also from GeoStats, is that you can vary this arrow length, also known as the lag, from 0 to a big value so that you see how this correlation coefficient changes as the arrow length increases. So let's start with the simple case where the head variable and the tail variable are the same. In this case, you see that when the lag is 0, I'm looking at the same pixel, I equals to j, and I have a perfect relationship between x and x, because they're sampled at the same pixel. If I start increasing my lag from a 0 lag to a lag that's positive, you see that the correlation coefficient, which is the inclination of this red line, it starts to decrease. It decreases such that it gets to a point where it's basically 0. There is no correlation anymore after the arrow length becomes too large. Let's go back to the 0 lag case and let's change the tail variable to y. Now, even though the two variables are sampled at the same pixel, these variables are different. So I have x in the horizontal axis and y in the vertical axis. Even though they're sampled at the same pixel, there is some scattering happening here. But the same behavior occurs when we increase the lag. So we can increase the lag from 0, and you see that this red line is going to start to become more and more horizontal to the point where you have no spatial correlation anymore. We can repeat this experiment with different images to see what it looks like. So let's go to the second image, 487. I think it's here. And you see that in this case, the image is in the United States, and it has very interesting channelized patterns here. The red and blue channel are now updated, and we see the original scatter plot at lag 0 shown here. The first thing you notice compared to the previous case is that this is a mixture distribution, right? You see a cloud of points here, and you see a lot of accumulation of points near the origin here. This is due to the fact that this image here has this big portion of dark color representing this water, and you have this rest of the image in another distribution. So that's the first thing that I wanted to highlight. It's a warning to show that spatial correlation in itself is not very informative of the complexity or the spatial distribution of patterns in the image. In this case, it still has some agreement with the mixture distribution, but you see in the next image that's not the case. We have again our arrow varying the image to produce a new data set, and you see that my scatter plot now changes as before, but in a different way. So instead of having that spherical point cloud around the center here in green, you see that the correlation becomes horizontal again as before, as we increase the lag. But there's always this amount of pixels here which live near the origin, and it makes this shape of the distribution of this scatter plot very different than the one we had before. Finally, to illustrate what I meant when I say that the RGB space is not trivial and cannot be straightforwardly used, let's go to this image 214. So image 214. So the image 214, as you can see, has this very distinct bluish color here. And the way that this looks like in RGB space is it's like a manifold looking shape. You see that my scatter plot now, even at lag 0, looks very different and very strange compared to the other ones. You see that the correlation coefficient or the regression line doesn't mean much in this case. We're not learning anything about the relationship, which is very complex here, of the process, but we're just feeding a regression line that tries to pass through these points and don't have any physical meaning. Look at how our age scatter plot looks now. We have our complex distribution of points, and as we increase the lag, we start to get that same situation where my correlation becomes 0 and near horizontal. So now that we have played a bit with a different set of images and we know more or less how this correlation coefficient behaves as a function of this lag or arrow length, we can move to the second step, which is defining coriagram and variogram. So we're going to define spatial correlation, which is the most common definition out there, as this Pearson correlation between the head variable and the tail variable. So if we study this correlation coefficient as a function of this lag, as we've shown with these interactive plots, we're going to produce what is known as the coriagram function, and this is the coriagram plot. It starts at maximum correlation when we are at the same pixel, and as we increase the arrow, we get smaller correlation until we get 0 correlation. So this coriagram is often a non-increasing function, and at age equals 0, as I was mentioning, we get this maximum correlation. In practice, this correlation goes to 0 as the lag goes to infinity. There are terms in the literature such as autocorrelogram when the head and tail variables are the same, and cross-correlogram when the variable at the head and tail are different. Correspondingly, we can define the autocovariance and the cross-covariance functions when we look at the corresponding covariance, which is just the non-normalized version of the correlation. Now we're going to work with a different statistic from GeoStats, which is in most cases equivalent to the covariance and correlation functions, but it's more general. The variogram statistic is computed this way, which is a different formula than the correlation coefficient. And you notice that this formula here uses this set n of age, which is the set of all pairs of pixels that are age units apart, to build this data set with pairs of pixels. And then we sum the square difference between what's in the variable I, the location I, and location j. So you see the first thing here is that this formula doesn't use the mean, the x bar and y bar that were present in the correlation coefficient formula. We can do the same for two variables, x and y, where we have this difference of x times the difference of y. And these two equations, they operate on this difference process, and that's why it's more general. When you do differences in a process, you kill trends, basically. So in general, you can think that this correlation coefficient is generalized by the variogram because it doesn't need to reach a plateau. It can increase indefinitely, especially when you have trends. So the variogram function, which is either the auto variogram or the cross variogram, it does not involve the mean of x or y, as I explained, and it's a measure of spread in the age scatter plot. So if you look at the age scatter plot that I was showing before, let me go back to something more reasonable to explain this. Let's pick image 68 again. So if I go back to image 68 and I look at this scatter plot, the variogram calculation, which is this difference between xi and xj, can be illustrated by this scatter plot. If you pick any point here, a sample which is a pair xy, yj, and you subtract this distance to the identity line, So what we're effectively doing in that variogram calculation is summing up the length of this vertical lines that go to these points compared to the identity line. So it measures how scattered this age scatter plot is at any leg. So this is the format of a variogram usually. So you have the coriagram, which is a non-increasing function, and you have the variogram, which is a flipped up version of the coriagram. At age equals 0, we have that this spread is 0, so you're looking at the same pixel usually, so your differences are zeroed out. And as you reach this infinity leg, you get this plateau here, which is known as the seal or the total variance of your process. So the term semi-variogram is also encountered in the literature, but many authors consider it to be outdated terminology. This semi-variogram comes from this half coefficient here in front of the variogram. But I myself consider this term to be outdated, as many other authors in geostatistics. So as I was telling, the variogram is connected to the covariogram and the coriagram in most cases by this relationship, which is just a flipped version of the covariance, where there's this covariance at 0, which is the seal of the variogram, to compensate for this flip. In order to understand why it's more general, it's, I think, too much detail and too much theoretical detail for this tutorial, but you can refer to the chapter 4 of Chile and Delfner, 2012, which explains the concept of RFK functions, intrinsic random function of order k. So now that we explained what this variogram function is, we need to build intuition about the possible components or parts or elements of this variogram. I would like to highlight the 4 elements of the variogram here. The first element is known as the range of the variogram. The range of the variogram controls the average radius of the blob shapes that you see in an image. So here what I produced at the bottom in this interaction here is an example where I play with the variogram parameters, and at the same time I create a random image according to this variogram model. So what I will do here is, as you see, I have some pre-filled pixels that I sampled at random just to make sure that all this realization look more or less the same around those pixels. And I'm gonna increase the range of the variogram to something bigger. As you can see, these blobs of yellows and blues are changing. I can make this range very small to the point where these blobs are very, very small. And if I make, for example, a range of 1, there is only 1 pixel of adjacency is connected to my current pixel in the arrow, I see that these blobs are basically of size 1, 2 pixels. And if I increase the range to a point where it is very large, you see that these blobs are very large as well. So I can say, for example, if I set my range to 10, that the average size of this blob is going to be 10 pixels. So you see this 10 pixels of correlation, 10 pixels of correlation, and so on. The second variable is, or element of the variogram, is the seal. The seal controls the amplitude or height of these blobs. Imagine that this is a valley, I don't know, in California, where you're seeing the mountains and valleys of this terrain. If you increase the seal, what you're going to get is higher and higher amplitude. So you're going to have deeper valleys and taller or higher mountains. And if you decrease the seal, you're going to have a more flat terrain. The third element is known as the nugget of the variogram. The nugget controls variability that's smaller than the scale of the image you're looking at. So if these pixels have a given scale, I don't know, in kilometers, in meters, anything that's below the scale is not measured or sampled when you look at the image at this resolution. So we can artificially introduce this nugget. For example, if I make nugget 0, I'm saying that my process is without any variability at the pixel level, but I can increase this nugget, which is the behavior near the origin, to introduce this white noise to the image, as you can see. And the more noise I add to the origin, the more I get to the close to the seal, which is the total variance, and my data set will look very salt and pepper, as is commonly called in image processing literature. So let me go back to zero nugget and explain the last and fourth element of the variogram, which is the variogram model type, which basically controls the behavior of the variogram near the origin. Here I have my Gaussian variogram chosen, and you see that it has this very smooth behavior when you interpolate these pixels. I can change this behavior to a spherical model, and you see that the increase in variance at very short distances is higher than the increase of the Gaussian. So the Gaussian variogram has this low increase of variability, whereas the spherical variogram has a higher increase. So because the increase is faster or sooner than the Gaussian, you see that the simulation of this spatial process looks more noisy than the Gaussian one. We still have the blobs of size 10 here, but the variability or the visual appealing or feeling you get when you look at this image is different than the Gaussian one. You can still add nugget to add even more noise at short scale, but you see that the picture is the same, right? So let's go back to nugget 0 and talk about a different example of model type, which is the exponential type. The exponential type increases even faster than the spherical model. So as you can see, we are going gradually here from a very smooth increase to an intermediate increase to a very exponential increase. So this exponential increase produces these types of spatial processes where you have this very bright localized features. For example, you have this very tiny blob here of very bright yellow, and you can keep playing with this, and you're going to see that there's, unlike the spherical model, there's always some bright spots in the image, and that's what basically characterizes this exponential model. So in order to solidify and to build intuition, I created this game on this notebook, which is the Variography game. And the game has the simple idea where we're going to look at an image without knowing what was the variogram used, and then we're going to try to guess the variogram by just looking at it. The code is very simple. I can unhide it here so that you see. I create a button called sample, and I bind this to a variable called sampled. And here in this cell, I create a random variogram. Whenever the sampled button is pressed, I rerun the cell, and what it does is it creates a model at random, which can be either of the three models we've seen, creates a range at random, which can be from 0 to 100 pixels in intervals of 1 pixel, create a seal from 0.1 to 1, and a nugget from 0 to the seal. And then I instantiate a variogram model at random. Here is another interactive element, which is the answer, which is a checkbox, which whenever I press this checkbox, I'm going to show the results here. So in this case, this image was generated with this exponential variogram model. The way I generate this image is also here, so we can look at it. It's following the GeoStats interface for problems and simulations. So what I do is I create a simulation problem over an image of size 600 by 300 pixels, where I simulate a variable called x of type float64, and I only ask for one image. It can generate hundreds of images like this. I create a solver, which is the FFT Gaussian solver, which takes the variogram model we created and solves the problem. After I solve the problem, I can plot the solution, and this is what we get. So anytime I press the sample button, I create a new variogram model and a new image. So I can sample again and I can play this game. So let's play this game together. What do you feel this variogram or spatial correlation model is here? How would you describe it in terms of the elements we have learned? It seems to me that it's not a Gaussian variogram, so we can exclude this model type, the Gaussian model type, because it's not smooth enough, right? So you see that there's a lot of patterns here that look more like the spherical or the exponential model. It's always hard to differentiate between spherical and exponential, but you see that the blobs of this spherical model are usually larger brights than the exponential one, which has smaller bright regions. Why the exponential has smaller bright regions? Let's recall here the expression of the variogram. We have this variance over differences, right? So if my exponential model is something that increases very quickly at short distances, it means that very close pixels are allowed to vary a lot. And you have those big bright spots. So I would guess that looking at this image, this may be a spherical model. Can you also tell anything about the range of this spatial correlation? I would guess that the size of these blobs is around, I don't know, 100 pixels, maybe a bit less, like 90 or something, 80, 90, or 100. We have here the range of the heights and lows of this image, which is equal to 3 sigma, the standard deviation. So I would say we have a standard deviation or CO that's smaller than 1 in this case. And it doesn't seem to have or contain that much nugget or that variability at the level of the pixel. So let's show the answer. Yeah, it's a spherical variogram. The range, as I was mentioning, is around 80, 90, or 100. There is no nugget, and that's it. So let's hide the answer and play one more time. Okay, this one looks like pure nugget to me. You don't see any clear pattern, and everything is very much like white noise. So I should see a nugget that's basically equal to the total seal. And indeed, despite the fact that this is exponential variogram, the nugget is equal to the seal, so I don't see any pattern. It's basically pure nugget effect. So let's play it one more time. Pure nugget. This looks like spherical again to me. Oh, exponential in this case, so it's hard, you see, to differentiate between the two. Okay, that's a tricky one. I would say that this looks like a smooth blob, but it's superimposed with some nuggets. So if I would guess, I'd say maybe a Gaussian variogram model with blobs of size again 100 or a bit less than 100, like 80-ish, and a lot of nugget. Yes, so it's a Gaussian smooth model with a lot of nugget, very close to the total seal, and a range of 95. Just one more example before we finish this tutorial. So here you see a different range out of the box. So you see that the blobs are much smaller than the blobs we're getting in the other samples. And it looks to me like this may be a spherical model again. I don't see, or maybe it's an exponential model. Definitely the range is something very small in this case, like 10 pixels of correlation. I don't know. But I'm really having a hard time to differentiate between spherical and exponential. I would go with spherical. Let's see. Oh, exponential. So one of the things that you also notice is that exponential model usually has this smaller uh, size blobs in general. So if I keep running this is a Gaussian, This is a Gaussian with a lot of nugget. This is a spherical model, and as you can see, like the blobs are usually, even though the range is 77, you have these small variations, but the blobs are more visible compared to an exponential model. Let's see if I find the exponential. And you see that the exponential model usually has this very smaller range property. So let's conclude this tutorial. So we have a few remarks. We really want to emphasize that understanding spatial correlation is key in geospatial applications. So if you are a professional or a researcher that's dealing with geospatial data and doing geospatial analysis, it's really important that you understand these concepts in depth. I highly recommend you playing with this variography game. The notebook is available for free online. It's open source and it's distributed along with the GeoStats project. And the project compiles a great list of variogram models so that you can explore. Here are a few models from the library of variogram models that's available in the GeoStats framework. I hope you enjoyed and see you in the next tutorial.